Okay, welcome this afternoon. Hope everybody's had their coffee, but you're not going to need it because we have got a great subject for everybody this afternoon. Propulsion system development for 2050 and beyond, 25 years from now. If we look back 25 years ago, we didn't even have the iPhone. We did not catch SpaceX rockets with chopsticks. We didn't have the F-35. The propulsion system was just getting started. So these gentlemen to my left are going to give you the vision for what propulsion systems are going to be like in 2050. And we have got a great group assembled, some a little more traditional than others, some a little more far out than others. Some that are developing systems that my grandkids are going to hop in and fly in taxis, I guess. I tell them never to get in them until I die because I think they're so risky. But anyway, they're going to convince us that they're not risky. I'm going to start one by one with this great panel. To my left, I've got Chris Harris. He leads propulsion technology development within the Research and Advanced Design Division of Northrop Grumman Aeronautics Systems. Chris is the program manager for the DARPA Ancillary X-Plane program. He's the propulsion lead on a serial hybrid electric aircraft development effort, and he was the functional air-breathing propulsion manager for Northrop Grumman. Over to you, Chris.
Yeah. All right. So I'm just going to stand up. It's a little easier for me. So thanks for having us out here. I'm going to talk a little bit about what I see as the future of propulsion based on my perspective. I think it's important to understand that everybody up here has completely different perspectives, but we're all informed by the same information. So I'm going to talk a little bit about what I see from the broad swath of technology development activities that are going on now, and why we can't wait till 2050 to start doing it because we don't have options anymore, really. So I'll start off by just talking about why we're gathered here today. So everybody in the room is gathered here today for a different reason. It might be just the air conditioning. It could be because you have a passion for propulsion like I do. I'm very interested in propulsion and aerospace engineering in general, but aviation is really what I care about deeply. I'll tell a little story. So when I was about 10 years old, I took one of those surveys, a career survey, that goes through, this huge multitude of questions, trying to find this balance between what you're good at, what you like to do. And, at the end, it gives you a few good options. And I skipped through the entire form, went right down to the bottom, and just wrote aerospace engineer, because I didn't want to do anything else. And it was partly because I love math and science. I was good at math and science. It was interesting. It feels like there's endless learning, and that's great. It felt important because I didn't travel until I was 16 years old on a commercial airliner. My parents have a lot of money. We just didn't travel often. And so I wanted to make aviation accessible, make it so affordable that people that really don't travel often can go experience the world, cultures, exciting places. I just always had this vision of that being what I wanted out of the future of aviation. And so I got on this path of propulsion engineering to get there. So, many years passed, and that was, kind of a long road. So I've been at Northrop for 17 years now. That's about 34,000 hours of time working. So I hope I like it. But that's led me to where I'm at today, where I see this possibility of now going away from what we're doing today, not only because, again, I think we have to, because we can't achieve that vision otherwise, but because now it's possible, and we're figuring things out kind of because we have to. To achieve the vision, really what the vision is to me is getting towards where we're achieving significant improvements in fuel consumption, and still we got to generate the thrust that the aerodynamics keep failing on eliminating the drag, so that we have to generate thrust. So as we go forward, what I think we're really aiming towards is significant improvements in SFC, and I'm talking probably half of what we're materializing today. And that really starts building into modularity. I think modularity and taking the gas generator out of a turbofan, pulling it out, and doing things completely differently is going to be the path forward for a wide class of aircraft. Now, every aircraft is going to have different requirements and different system requirements, but we got to start thinking of and doing basically what the electronics industry is doing, standardizing interfaces, high degree of modularity, and increasing that modularity over time. And there will be different levels of that modularity, but the first interface that I think we're going to start working, which is really happening now, is through hybrid electric, but it's really about the interface and that modularity, is separating the generation of thrust from power. And once you take, and the reason why is I think pretty clear, but the reason why is really because you want to take that gas generator out and take something from the 30-ish% lower heating value efficiency from fuel to power and achieve something like 60. And I think that is now doable. I think there's paths to that. When I was 10 years old, I didn't see a path. I had no idea what this path would look like. I had no notion of what that even looked like. But now I'm seeing, and I believe that there is very clear paths to achieving roughly double the efficiency of power plants, as we're seeing today. And why is that important? So I work for Northrop Grumman, so I work on power plant efficiency and mission capability. Those both go hand in hand. So from a Northrop Grumman perspective, the value in that is essentially going from those levels of increase in efficiency can roughly triple the amount of payload we can carry on an aircraft. And when you think about the job of an aircraft, it's to get a certain amount of payload to a certain place at a certain time. So that is a huge increase in the capability and efficiency and the value of aircraft systems, and the level of capability we can then integrate into an aircraft will be dramatically different. So why do we have to do it today? Why are we here? I think primarily centers around the asymptotic nature of the Brayton cycle. And what we're doing is we are out in the flats of thermal efficiency. So every dollar we spend on increasing material properties to take higher temperatures and move farther out on that asymptotic curve gets less return, and we've done an awesome job. And so every dollar achieves less delta T because we're already at such a high temperature that going to even higher temperatures is even harder. So we've gotten to the point where we've done that. We're fighting bypass ratio. For military aircraft systems, there's only so high a bypass ratio you can go anyways before it trades off the vehicle. But even for commercial aircraft, most of the efficiency and the fuel burn benefits have come from increasing that bypass ratio, but we can't continue doing that. We're getting to these limits. The one limit that I think we haven't seen yet and that I think is going to be really important is taking our fuel to power efficiencies up by breaking those interfaces and creating new interfaces, which I believe is hybrid electric, and having an electrical interface which has a myriad of other benefits towards developing programs and actually achieving value for our customers. And I'll tell a quick story, so I think I'm going a bit long.
You are.
Quick story is that I was working a program, and it was an electric aircraft program, hybrid electric. It ran into issues. We tried numbers of different power plants. There's continued to be issues, and we finally went to a backup solution, which was, and each of these is a different number and different type, different cycle, completely different types of power plants combined in different ways. Had we had to redesign the flow path and the aerodynamics of the vehicle and reintegrate everything, redesign the stability and control database, the aerodynamic database, the propulsion database every time, that program would have died. So from an investment perspective, I believe there's a lot of important benefits to this modularity to customers for a huge number of reasons, but also on the investment side. So I think this is a really interesting time that's going to get us to significantly better and investable technologies that are going to achieve that kind of vision that really makes a significant improvement in how we we travel, how we fly. So thanks for the time. I'll pass it on to
All right. Thanks, Chris.
Thank you.
Okay, our next panel member is Dr. Wally Arisimolu. He is currently the Associate Director for Advanced Concepts and Technologies at Pratt & Whitney, division of the RTX Corporation. In this role, he has responsibility for identifying, prioritizing, planning, and maturing technologies for the next generation of advanced propulsion systems to ensure timely readiness for product insertion. Wally is an associate fellow for AIAA, a member of the American Society of Mechanical Engineers, and a member of the SAE, including its G11 Committee on Probabilistic Methods. Wally, give us your thoughts.
Yeah, thank you. Yeah, good afternoon. It's actually a pleasure to be here. I just want to start by saying Pratt & Whitney celebrated its 100th year anniversary yesterday, July 20. Yeah. Thank you. So we have 100-year legacy of innovation in propulsion systems and building dependable engines, not only for commercial flight, but also for our military systems to make sure we protect and defend our freedom. So we're very proud of that legacy. As you will see, dependable engines are important to the success of commercial and military flight. We have robust technology roadmaps that we develop to ensure that we're ready for the next generation and the generation after next propulsion systems, because these technologies take a long time to develop. And I'm fortunate enough to be in an organization where my primary role is to think about propulsion systems of the future. 2050 may sound very far away, but in the aerospace world, 2050 is very, very close indeed, because these technologies take a long time to develop. You will see what I flashed up here is a suite of technologies that we develop, because we don't believe there's only one single answer to getting ready for the challenges of 2050 and beyond. On the first line there, you will see the continuous improvement of current engines that are flying, and making sure that any opportunity we have to improve the technology, we actually do so and mature the technology. That's important because that's what we have been doing for the last 100 years, and that's what we continue to do for the next 100 years. And the second part of this, you will see electrified aircraft propulsion. We develop electrified aircraft propulsion to give us additional knobs that we can turn to make sure that we improve efficiencies in other ways, other than the conventional ways of improving SFC of the gas turbine engine itself. And then on the third line, you see hydrogen. Hydrogen is a fuel that provides potential opportunity for leveraging in terms of its chemical storage characteristics as well as its proper thermodynamic properties that will allow us to utilize cycles other than the conventional braking cycle to improve the overall efficiency of the engine and of the whole propulsion system. You also see that you had a session this morning about the utilization of SAF, synthetic aviation fuel or sustainable aviation fuel. It's also one of the areas where we can improve efficiency as well as emissions by utilizing that kind of fuel. And finally, we continue to work diligently to improve other kinds of emissions apart from CO2 emissions, but also improve the noise footprint of propulsion systems, because as we have more aircraft flying, in our areas, we have more complaints about noise. Those who live around airports know the importance of this. One of the single most popular complaints about aircraft in populated areas is noise flying over. So those who live near airport worry about this. Now, my colleagues will talk a lot more about hybrid electric propulsion. But I want you to know that at Pratt & Whitney, we are doing a lot of work on hybrid electric propulsion, spanning the whole envelope of applications, from small-scale applications of urban air mobility all the way to single-aisle and larger aircraft. And you can see examples of what we are doing there on eVTOL size, working with Airbus on the helicopter side for hybrid electric propulsion. Also, our Pratt & Whitney Canada division working on regional aircraft, parallel hybrid electric aircraft, and with single-aisle class aircraft, also working on hybrid electric propulsion, again, parallel hybrid propulsion. And this work we are doing in partnership with people from all over the world, including, of course, Europe. So this is hybrid electric propulsion is a big part of our plans for the future, both the immediate future and the far future, where they can be synergistically combined with other technologies I showed to you. Hydrogen has many characteristics, and we are doing work on hydrogen applications for combustion. We started work on hydrogen. We did work on hydrogen back in the 1950s. We developed the so-called Suntan engine, which was intended for a military application by then. We didn't go to production with that. But recently, we have been doing work on hydrogen. You might have heard about HySite, hydrogen steam injected intercooled turbine engine, and also our Pratt & Whitney Canada division working on a program called HyAIDIS, all of hydrogen. This utilizes unique properties of hydrogen to change the cycle from a conventional breathing cycle to a better cycle that provides substantially higher efficiency at all points of the operating envelope. Okay, so I won't talk too much about this, but it's to say that we leverage the properties by actually recovering the water from the exhaust, which actually has a higher quantity of water because of the chemistry of combustion of hydrogen produces more water than you will get from a conventional jet fuel. We use that water for cooling the compressor, and we inject into the combustor, essentially eliminating NOx. We have conducted tests to show that NOx is virtually eliminated, 98% reduction. We have also conducted tests to show the recovery of water successfully done, and also that the combustor can operate at very high steam to air ratios. So that's very exciting work that we're doing, and we are proud of continuing to explore. We're also working on the multi-fuel propulsion concept approach, a multi-fuel approach whereby you have both hydrogen and conventional jet fuel in an aircraft, and what you do is that you provide yourself the flexibility to utilize either hydrogen or jet fuel, depending on which airport you are flying to and depending on which fuel is available at that airport. We feel this is important. It's going to provide a very, very nice and smooth transition, from this jet fuel-dominated energy content to a potential hydrogen future. So that's important. We believe this will provide a very important way for us to safely and smoothly transition to a hydrogen economy when we decide to do so. Finally, I want to say there are other important technologies that you may call enabling technologies that will allow us to develop these propulsion systems into the future. Modeling and simulation is a big part of it, especially the use of high-performance computing. Things like graphical processing units, GPUs, are very important. Machine learning and artificial intelligence, very important. And use those in combination with multi-physics models and multidisciplinary optimization algorithms that allow you to select the best designs to optimize whatever the objective function will be. Also, in terms of designing materials, such as high entropy alloys that will allow you to achieve higher material temperatures to be able to operate your cycle in a way that still provides appropriate level of durability for your applications. It's also going to be very important in the future. Also, in a third area that we have been working on is advanced manufacturing that would ensure that we can produce the propulsion systems we design at rates, because you have had from Airbus and Boeing their desire to produce about 70 aircraft per month, but right now for the tube and wing airplanes you see in commercial flight, every aircraft requires 2 engines. So if they're going to be produced that many aircraft, we have to produce twice as many engines that will go with those aircraft as well. So these are some of the things that are guiding the development of propulsion systems for the next 25, 30 years. And we'll be glad to have more discussion about that. Thank you.
Thanks, Wally.
Okay.
Okay, our next panel member is Eric Barch. He is CEO and co-founder of Vertigo Aero, a global leader in aerospace hybrid electric propulsion. Vertigo Aero focuses on high-performance hybrid electric systems that enable electrified aircraft to have significant mission capabilities. Eric led development, flight testing, and marketing of one of the early battery mission capabilities, battery electric aircraft programs, and he was responsible for the first electric aircraft formation demonstration team at AirVenture 2013, a dozen years ago. He holds more than 20 U.S. patents and is rated as a commercial instrument, airplane, and glider pilot with flight experience piloting electric aircraft. After more than 30 years of fixed-wing flying, he's also recently become a student pilot in helicopters. Eric, over to you.
All right, thank you. Glad to be here today, and I wanted to first put the audience to work a little bit, so apologies for that, but can you raise your hand if you took an airplane to get here? And keep your hand up. All right, way up, all right. All right, now put your hand down if you only flew that airplane for less than 100 miles. If you flew more than 100 miles, put your hand down. Flew less than 100 miles, okay. All right, hands back up for those of you that flew airplanes. So who flew an airplane? All right, how many of you traveled with absolutely no luggage? Okay, didn't think so. All right, now hands back up. One final question, I promise I'm not gonna work you too hard. If you flew an airplane, hands up. All right, if you never went faster than 200 miles an hour, keep your hand up. That's kind of what I thought. So the point that I'm making there, and this is a point that's the general market, is that for the most useful things that we all do with aviation and for the big core of the market when we think about 2050, we like to go fast, we like to go far, and we like to take a lot of payload with us. And that tends to be the core market for aviation and the things that drive the biggest adoption across the world. That isn't to say that a lot of us, myself included, haven't worked on things that violate those principles. But when I'm talking today, for the topic at hand about trends that are going to impact the big picture in 2050, I really wanted to think about what is going to impact that big core of the market. So there are a lot of really interesting things we can do with electrification. And when I talk about electrification, I'm talking broadly about electrification. So that doesn't mean batteries, that means there's propulsive electricity on board the aircraft. And there are a lot of interesting things that are being done and a lot of compelling things that are being done with electricity for propulsion. That leads to new types of aircraft, new configurations, new missions. The middle pictures here I would classify as new things that spin and make thrust. And there's some really cool things that you can do with electricity that you can't do with a turbine or piston engine that allow you to make thrust in different ways and use the benefits of electric power distribution and electric motors. And then we've got a lot of existing military and regional airline markets where there are also people working on electrification. And so electrification is a very broad field, and I would encourage everyone, don't think of electrification as batteries. Think of electrification as any of the ways we're using electricity to create thrust. So that leads to a really, really important question, and that is, how do we package the energy that goes on board these aircraft? And there are three primary ways that we look at doing that in the electrification space. One is the battery pack, one is hydrogen, either gaseous or liquid, and one is liquid fuels like jet fuel or SAF. These all have different attributes and different trends that are going to be critical over the next 25 years. And they all play out a little bit differently, and they're all relevant to electrification. So the first one I want to tackle is batteries. And those of you who may have seen me talk in the past, this graph is a modified version of what I have referred to lovingly as my personal battery disappointment curve. As was mentioned in my introduction, I've been doing electric aircraft, along with Mark anyway, since before it was cool. And I've had a lot of promises made of things just around the corner. You're going to be able to buy this next year. This is about to be on the market. And then there's the curve that's what I actually could buy every year. That's that kind of flat red line that's actually taken a bend downward in recent years. So battery electric storage of energy or packaging of energy is going to happen. It is happening. I'm not saying that it's not going to happen. But if we look at where that's going by 2050, it's not going up fast enough in energy density to take on that big core group of missions that you all raised your hands for. And therefore, we have to look elsewhere when we think about how is the energy going to be packaged. When we think about hydrogen, hydrogen is a lot easier to get the math to close when it comes to how you make an airplane fly on hydrogen and have significant mission capability. Not that I'm implying that any of these things are easy, but there's a difference between very, very hard and impossible, and this falls in the very, very hard but possible category. The challenge with hydrogen is more one, as I see it, of infrastructure availability. And if I look back at the auto industry for the last 25 years, I ran across some data where in the US market, we've gone from 5 fueling stations to 60 fueling stations in 25 years. Now that's for consumer hydrogen. There are more than that for commercial hydrogen, but it's not a big number. And so there's a bit of a chicken and egg thing going on with hydrogen, where if that's how you package your energy, you have to have airplanes that are designed potentially before there's infrastructure, or you have to have people investing in infrastructure before there are airplanes wanting to buy the hydrogen. And the result is that we're going to see hydrogen. I think over the next 25 years it's going to happen, but it's going to be in geographic pockets and market segment pockets around the world. And those may be significant in themselves, but they're not the big middle of the market. And so that leads me to liquid fuels. And that's both sustainable aviation fuels, which we all love because that's the future, as well as jet fuel, which we love a little less, but I'm guessing that almost every single one of us use jet fuel to get here and to get home. So with sustainable fuels, the trend has been a lot better when it comes to the rate that those are going into service. Not that they're moving at close to the rate that we need for all of the market to go to SAF, but I think if those of you who were in the early presentation today saw, we don't really need this to move any faster than ethanol moved when it went into service, and that did scale up and in fact got quite significant. So the great thing about sustainable fuels, though, is that they're backward compatible with jet fuel. So if we use liquid fuel to store the energy or package the energy on board an electric aircraft, we're compatible with all the current infrastructure, and we're also compatible with SAF, which is one of the biggest trends in sustainability. And so that really gets us to hybrid electric, because hybrid electric is the thing that links the sustainable fuels or the current non-sustainable fuels to the ability to do all the cool things with electrification that we want to do, whether that's new types of aircraft or designs of aircraft, or whether that's new types of propulsors that are going onto those aircraft. So as I look out at 2050, I think it's not a matter of which one of these things will happen. They're all going to happen. They all already are happening. But we need to think about what are the rate limiting factors in each one of them, and that does favor the liquid fuels being a larger part of the market even as far out as 2050 and beyond versus some of the other options. So at this point, I'd like to switch over to a really quick video that will show you some of the hardware that is currently under development and in fact is flying behind the scenes in some manned test aircraft, just to give you an idea of where the hybrid market is and where it's going next. Thank you, and we can roll a video. The VH4T turbine hybrid power plant is the highest performance system on the market right now. Using the Pratt & Whitney turbine and Vertigo's proprietary hybridization technologies that are built around it, we've got a new type of power plant that delivers onboard propulsive electricity at 800 volts DC and 400 kilowatts continuous power output. You can think about replacing the huge battery pack with this 550-pound, 400 kilowatt power generation system, a much smaller battery pack, and a fuel tank of either jet fuel or sustainable aviation fuel. And what that gets you is up to 10 times the range, higher cruise speed, and more payload. There are a lot of missions where the military needs to go very long range, and they need to go all the way out and come all the way back. Let's say an urban air mobility aircraft. You may be able to take that range up by a factor of 10 while also taking the cruise speed up by 20 to 30% and taking the payload up. We're powering the electric flight revolution. So we can use these next generation liquid fuels, run them through the VH4T, and power the electric motors in a next generation aircraft and get all of the benefits of the two most exciting revolutions in sustainable aviation. Hybrid electric is going to be the right solution that gets us the next generation of aircraft that are more efficient, lower cost, longer range, higher performance, and safer. Thank you.
Thanks, Eric. Okay, next panel member, Mark Moore. Mark is the CEO of Whisper Aero, a venture capital funded startup developing the next generation of distributed electric propulsion. Mark co-founded Uber Elevate as engineering director during the 4 years Uber pioneered the urban air mobility ecosystem. Prior to this, he led NASA's foundational development of DEP during the last 10 of his 32 years of his NASA career that specialized in VTOL and CTOL technologies and concepts. And that research included leading the Puffin, GL-10, LeapTech, and X-57 Scepter, the first NASA manned X-plane in over 25 years. Mark?
Cool, thank you. So, I'm going to talk about the big picture of aviation propulsion, and I'm going to talk about electric propulsion, and I'm going to ask something of you. And that is, right up front, I'm going to ask you this what-if question that I want you to be thinking about during the few minutes that I'm presenting. And that is, what if you had a new magical aviation propulsion widget that could violate, change, disrupt two truths that have been present in aviation for the last 80 years? And that is, what if a larger engine or a larger thrust device was not any better than a tiny little one? What if you could have this widget that is scale independent in terms of the weight, the efficiency, all those characteristics that you care about? Right now it doesn't exist, right? And what if, instead of integrating propulsion as an isolated disciplinary solution, like it's basically been my entire 40 years at NASA in private industry, what if all of a sudden there were the tools, the processes, the capabilities, and the team environment to design aircraft in truly multidisciplinary ways, where you can have the acoustics and the structures and the propulsion and the aero all being worked in very, very tight harmony. So just imagine, right? We're all engineers, so turn down the skepticism, the healthy skepticism that we all have in our brains, and dial up the imagination. What would you do with that? Would aircraft just look the same if we had this abrupt change of two truths? Or would they look different? So I'm going to start with this big picture where, hey, we've been in the combustion era, the hydrocarbon era for the last 80 years. And so this is the truth that we've been marching along in our path of thermal efficiency versus propulsion efficiency, where we started at turbojets, moved up to low bypass ratio fans, moved up to high bypass ratio fans, and now the industry is focusing on really high bypass ratio fans, right? Where we're trying to squeeze every little bit of fuel by going to higher pressure ratios and more fan air, less combustion air. So all of a sudden, if you're doing things with electric, and just ignore where the energy is coming from, right? Eric is solving that problem. All we care about is how we're generating the thrust. So whether it's a fuel cell from ZeroAvia, or the latest battery, or a turbo generator from Pratt, they're all just providing electricity. And so what we care about is, how do we best generate thrust from that electricity? And so what this plot is what really matters now that you don't have combustion. There is no thermal efficiency anymore. You're not burning anything. So now what matters is that fan pressure ratio. And when you were burning fuel, it really made sense to start with conventional turbofans, where you have a very high fan pressure ratio, because you want as much pressure in that air to be able to burn it efficiently as possible. So that's where it started. But if you look across that Mach number and these propulsive efficiencies at these different colors, you realize conventional turbofans were far from the best propulsive efficiency solution. And even if you go to the current great geared turbofans that Pratt makes, they're still not at the fan pressure ratio that gets you to the optimal propulsive efficiency. You have to actually be increasing the bypass ratio or decreasing the fan pressure ratio to do things like open rotors that you can see there for the CFM rise, or electric ducted fans that are able to be at that 1.2 fan pressure ratio solution. So in this era where we do, as Chris said, we can separate the boundaries of the energetics from the propulsion, there's really a different problem that we're solving. And one of the challenges is when you go to these really low fan pressure ratios is they get big. So whether it's the CFM rise solution, those are pretty darn big rotors because you got a lot of move a lot of air because the pressurization that fan is doing is less and less. So you need more and more surface area. And it gets harder and harder to integrate those under the wing. And it's not just the propulsors that matter. How you integrate them really matters. And so essentially by going to these lower fan pressure ratios, which is 100%, you're not going to hear any of us say differently. The future is lower fan pressure ratios, higher bypass ratios, even if you're burning fuel. It gets harder and harder to integrate them. And so then you see, for instance, from Green Jets, you see these great big ducted electric fans, and you see that they're really big, which creates a lot of extra weight and a lot of extra drag in these ducts, which makes them not so great to integrate, especially on the wing, but it makes it really, really challenging. So now we go back to that what if question of what if you had a scale invariant, scale independent propulsion solution, and the specific thrust and the fan efficiency is invariant. It's the same whether it's a 3-inch electric ducted fan or a 3-foot electric ducted fan. Well, that is what Whisper Aero has done. And we're the first to be able to do that or claim it. That is, even if we're doing a little leaf blower, which we are doing because it's ultra quiet and very, very efficient, it has the same 90% fan as our great big aerospace propulsors. And it's a really, really simple propulsor. We don't have to embrace gearing or liquid cooling, but we can go to this really simple device that only has 2 moving parts, bearings and fan, the fan itself. And if you compare that to the bottom figure, which is a conventional turbofan, you can think of it sort of as that turbofan is a serial device. It has a fan, compressors, 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 turbines, 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 all dependent on each other in that one device. Well, what we've done is we just have one fan. And so what we're doing is parallelizing thrust, because it is no better to have one big propulsor than 20 small ones. And in fact, the beauty is that with these small propulsors, they can cost 1/4 per pound of thrust of what the big ones. Because when you go big, you go to exotic materials that are highly stressed. And when you go small, you can use manufacturing processes that are much, much cheaper. And you can go to materials that are far less stressed. So all of a sudden, you can be doing crazy things, like you see on the aircraft on the bottom right. And guess what? It's not crazy. It actually makes more sense to distribute these propulsors, because not only do you not have any penalties on the individual propulsor, but you have synergistic integration gains as you embed them into the wing itself, whether to decrease the wing area and to be able to cruise faster, or to be able to take off and land in a shorter distance. And for this specific implementation, this goes back to how I started my career at NASA 40 years ago, where the first 5 years was focused on this aircraft, the Quiet Short Haul Research Aircraft, the QSRA, which pioneered a thing called upper surface blowing. And it's a magical thing that creates lots of extra lift at low speed conditions and doesn't cause any additional drag at high speed conditions, unless you have those great big bulky turbines that are sticking out, which now can be replaced with really compact electric ducted fans that are buried into the wing itself. So there's no extra external wetted area. There's no additional weight or drag associated with that external ducting. So it really is a very exciting time where we have these disruptive technologies that let us design aircraft fundamentally differently, whether it's for drones where we use a single propulsor that can fly very close overhead and you can't hear a thing because these propulsors are also ultra quiet as well as very, very high efficiency, or carry much more payload on a glider and make it a powered glider that can do the same. Both of these have been done and are being done right now at Whisper Aero, or this future where you can have aircraft not only small, but even up to airliners that can dramatically increase performance at a much lower cost because of this new disruptive technology. Thank you very much.
Thanks, Mark. I know y'all are anxious to ask some questions, so go ahead. You can start loading them in. I know y'all all know how to do that by now. We're going to ask those right after our last panel member. Vadim Belogorodsky is the head of application engineering at Zoravia, a leading developer of hydrogen and electric aviation propulsion technologies. In 2018, as an early employee, I think it was employee number 004 at Zoravia, Vadim partook in the world first electric flight of a 6-seat aircraft. Since then, Vadim has been focused on fuel cell development for both low temperature and high temperature applications, fuel cell system integration into vehicles, and hydrogen refueling infrastructure. Vadim, give us your perspectives.
Thank you. Hello, everyone. So my name is Vadim. Thank you, JD. My story started with ZeroAvia back in 2018 when the CEO, Val Miftakov, came to me, I believe it was a LinkedIn message, and he said, I need you with your skill set. We're looking to start a company. We're going to do clean aviation. I replied, is this a bot? He said, no, let me call you. Gave him my cell phone number, and I think I was in California the next week, and we were talking about ZeroAvia. So the purpose of ZeroAvia is to share the climate impact and decarbonize aviation. Without technology to tackle all the climate impact, it'll kind of lead to an existential crisis for the industry, and it'll curb demand while making aviation less accessible to everyone else. We believe that hydrogen electric propulsion is the only path to truly sustainable flight. And I'm here to tell you how we're going to do that. So we have 2 major sites, one in Everett, Washington, and one in England, in Kemble. And our track record of what we've done to date, the first image in 2018, we built an electric motor ground test demo on top of an El Camino, and we drove this around the streets of San Carlos just to prove that electric motors were robust enough to kind of survive the duty cycle that we wanted to see. Less than 10 months later, we retrofitted a Piper Malibu with that same exact drivetrain, and we flew it around Hollister, California. The CEO was the pilot, and I was the test engineer sitting next to him. So then in 2020, we did the world's largest hydrogen electric flight with a Dornier 228 in England. Sorry, that was with the Piper Malibu. In 2021, we did the same with the Dornier. In 2022, we did the first airport refueling with hydrogen. And from there, we've just grown. We've since started development of our own high temperature fuel cell program. And we've sold our first drivetrains, including our EPS, our electronic propulsion system units, and fuel cell units, PGS, power generation systems. Along those lines, we're also engaged with the FAA and the CAA towards our certification intent. And so we've just recently received our FAA G1, which is the basis of understanding towards certification. The next step will be the FAA G2, which is the means of compliance. And so we're steadily along the way to bring hydrogen to reality. With that, we have some examples of our drivetrains. So the ZA600 is a low temperature fuel cell based system. There's a ZA600 motor that can produce 660 kilowatts, and that is with 4 inverters. So to look at some of the redundancy there, we have 4 quadrants of the motor and 4 inverters. Those are powered by multiple fuel cell modules. Next to that is the ZA2000 meant for regional aircraft. And that is a high temperature fuel cell based technology. With that, we're looking at applications like the Dornier 228 and the Dash 8. Alongside that, we also have some of the refuelers that you see on the bottom right-hand side. So those are both gaseous and liquid refuelers. And so by 2050, we believe that we can reduce about 1 gigaton of CO2 and save operators about $40 billion. On the path to this, we had some commercial agreements. We have investments from 4 of the world's top 10 largest airlines, United, Alaska, IAG, and most recently American agreed to commit to engine purchases. With that, we have over 2,000 engines in commercial traction. So between that and some of the other technology and partners, we're looking to bring some of the technologies to market. We just finished our Series C raise, and we have some government grants that were awarded to us, which tells us that we have a viable product. There's some due diligence involved in all of these names, and they all believe in us and we believe in them. And so what does propulsion and aviation look like in 2050? We believe that it'll be based on liquid hydrogen storage. That'll be cryogenic at about negative 253 Celsius. The power generation will be provided by high temperature fuel cells. These are direct air cooled. And the propulsion will be based on electric motors with built-in inverters. The combination of all 3 of these are being done by ZeroAvia at the moment, so we're fully vertically integrated in our technology stack. We have partnerships to develop the liquid hydrogen systems. We're developing high temperature fuel cells with industry partners, and we're developing the electric motors and inverters in-house. That's all I have for that. Thank you, JD.
All right, thanks, Vadim. Appreciate it very much. Okay, we're going to start with some questions from the audience. Please use your app to vote up on questions and add whatever you want. As we told you, we had a pretty diverse group, and we got a diverse group of questions here. And You know, I've worked on fighter aircraft my entire career, so I told Wally he was going to get a question on this. So maybe this is split between my Northrop Grumman and Pratt & Whitney partner. So Chris and Wally, maybe what are your thoughts on propulsion systems for fighters and bombers in 2050? Will there be any difference between those two, do you think?
Well, yeah, I'll just start by saying I think fighters and bombers are significantly different classes of aircraft. I think when I was talking before about what I see as probably the biggest element of propulsion in 2050, you know, what's advancing and going to make the most significant impact, that's really focused on transonic and lower speed aircraft. I don't think in the near term it's going to advance enough to be applicable to combat aircraft, to fighter aircraft. But I do think there's going to be continued emphasis on the modularity piece and variable cycles as being an important element of what's going to be needed for the combat aircraft side.
Great. What anything?
Yeah, thanks for the question. You know, I agree with Chris in what he has said, but I think you should look at what is expected to be the battlefield, you know, in 2050 and beyond. The propulsion system is not just there to deliver thrust. It's delivering a lot of other things. You know, it's producing a lot of power for use for the weapons, and it's also going to be operating in an environment where it has to communicate extensively with surrounding assets. So I would say artificial intelligence, automation is going to be a big part, especially for fighters. They have to have the ability to interact with surrounding elements in the combat zone, and they have to continue to use adaptive propulsion so that the parameters of the propulsion system can be adapted to the particular domain of flight they're in. I think that's going to be a big difference. I'm sure many of you have heard about work the U.S. Defense Department is doing on collaborative combat aircraft. You know, is to make sure that there's no reliance on the single fighter, but the single fighter that operates in an environment that consists of other important elements that support the mission.
Right.
Yeah.
Can I add a disruptive thought?
Yeah.
I think it will be completely different. And Ukraine is the proof point. I think these $300 million to $1 billion fighters and large centralized aircraft will be replaced with distribution. And that distribution is not just an airframe architecture theme, but that you will see the ability to have thousands of very effective drones that are far more effective than one fighter or one bomber. Now, certainly there's a lot of different missions to cover, but distribution and swarming are going to be a huge theme across both those mission sets.
So I'll add on to Mark before you go, Eric.
Okay, go ahead.
So as somebody who's developing a small hybrid electric long endurance vertical takeoff and landing aircraft, I completely agree that, so the trend that we've seen, and it's great if you look up this plot on Google showing the proliferation of the number of launches of satellites. It is completely exponential starting around, I think, 2017, 18. Capabilities are getting much smaller, payloads are increasing in capability, and we're figuring out how to really make small aircraft much more useful by extending the range. I don't think replace is the right word. I think they're going to significantly offset the number of large systems required, but there are certain payloads that will have to go far. I think we're going to extend our capability and offset the need for as many large systems.
Your B-2 did a very, very impressive job last month. It was led by Lockheed Martin F-22s and F-35s, but it did a fantastic job, and I've got to give Northrop Grumman credit for that. And it did carry a very, very large set of weapons and took a big airplane to do that.
Back over to Eric if you want to final
Anyway,
thought.
Eric, your thoughts?
I guess one thought that actually builds on both pieces of that is, I think one trend that we're seeing is a strong desire for runway and infrastructure independence, and that plays out differently in the small versus the big. But as you have aircraft that want to have transitioning flight modes where they may need to take off and land vertically, hover, and also cruise at a very high speed, that is going to require some propulsion innovation, certainly. And I think a lot of the things that we're working on collectively here wind up helping to address that, whether it's at the small swarming drone end of the market, which I do believe is going to be a major factor, or whether there's a more limited number of large, high-value assets that are also using that same strategy.
Okay, we'll switch topics. The number one rated question, with these new innovations in propulsion, is there a need to retrain pilots based on the fuel type, mixture, power control?
So I'm going to speak as someone who's flown electric aircraft and who actually had to work a lot on battery fuel gauges to figure out how to do that, and ultimately we didn't quite figure out how to do that. It's hard. So when you're talking about I will say it's hard if the battery is the primary energy storage means on the aircraft. Batteries can play a lot of roles. You could probably write a large book on all of the different ways you could leverage batteries in different types of missions. If the battery is the primary place that your energy for your mission is stored, that becomes really tough, because it's like you've got a fuel tank that changes its size depending on how much it's been used in the past, what the temperature is, how fast you're pulling, energy out of it, all of those things. So there is definitely a pilot training aspect of this. I don't think it's an insurmountable thing. It is really hard, and I say that as someone where there was a couple of year period where we were putting some really good people on that. We had some good ways of providing information to the pilot about the state of energy on board the aircraft, but it's not what people are used to when it just comes to gallons in the tank.
May I be disruptive again?
Please.
Yes.
Look, the pace of autonomy research is insane. And the amount of money going into autonomous systems, is equally insane. Mm-hmm. We're talking 25 years from now. Autonomy will be omnipresent, not just in cars, but certainly in aircraft. So pilots will be retrained to be ground assistants.
May I add?
So
with hydrogen, for example, right? Like Eric said, that batteries are hard to level their state of charge. Hydrogen, for example, has a known pressure, right? You can read the pressure of a tank. You know how much you've used. We have engaged the FAA on pilot training. We've engaged maintenance crews on new things that they would have to learn. But ultimately, our goal is to make it as seamless as possible to jump from one technology to the other for the pilot. We take that on ourselves. I also think, as Mark said, in 25 years, you'll have a new generation of pilots, right? They'll be used to looking at 10 things on a screen at once rather than, gauges, seeing gauges.
I like to tell all my Lockheed Martin F-35 pilots that when you hover, we don't ask you to do anything. We ask you to fold your hands because you don't have to touch anything. But anyway, you're right. 25 years from now with autonomy, there are so many things that are going to be automated that I'm sure with these unique propulsion systems, it'll be the same thing. What if we switch from the pilots to the the maintainers maybe on the ground. Vadim, this would be for you. What additional aviation risks are associated with hydrogen cryogenic storage?
Sure.
What happens if the cryogenic storage system fails?
That's great. It's a great question. We get this all the time. Quite frankly, if it fails, the hydrogen heats up. It simply evaporates. Being the smallest molecule in the universe, it'll just dissipate into the atmosphere quicker than, aside from an open flame, for example, it's very safe to vent hydrogen. That's kind of the worst case scenario of a cryogenic system. But of course, we have multiple levels of safety to prevent that in the first place. And the hope is that it never gets to that.
Great.
Yeah,
Anything?
I would say, safety is number one priority, no matter what technology you are using. And we have said that the expectation for the aerospace industry is that any technology you introduce will produce the same or better levels of safety and reliability. Nobody is ready to accept a technology that is going to go backward in terms of safety. So the good thing is that there is some experience with handling hydrogen. For example, at NASA Glenn Research Center, they have developed some training packages for how to handle hydrogen, and because they have used it in other applications, and I think the industry will benefit from making sure due attention is paid to that aspect. And also the certification agencies like FAA and EASA are working on that to make sure they are prepared to develop certification guidelines that will make sure the use of such fuels are still safe compared to what we have today.
Yeah.
So I guess I'll take a counterpoint to that, and I know it's, especially in an aerospace audience, and I'm a pilot, it's kind of heresy to say that safety has to be paramount and it has to be number one. But now I'm going to bring in something that Mark said, autonomy, and swarms of drones that may not have people on board. We actually can't assume that all of these new things in all situations need, let's say, Part 25 levels of safety and reliability. And if we do that, we're going to saddle ourselves with a burden of regulatory oversight that is probably going to stifle progress. So if you're talking about a commercial narrow-body airliner,
exactly.
I totally agree.
Yes.
We need a very high level of safety.
Yeah.
If you're talking about a 200-pound drone that is swarming for military use, there are going to be all kinds of risks that you can take on that. And there is probably a continuum of, different safety levels. And in fact, in the regulations, there is a continuum. So I think it's important to remind ourselves that there isn't just one level of safety. We don't want to take passenger safety backwards for commercial flight. That's absolutely the case.
Exactly.
But we also don't want to saddle new innovations with the burden of having to be done at that level from day one, or we won't get anywhere.
And if you think that certification is going to block all these technologies, then think what just happened the other day, where, believe it or not, the FAA signed Mosaic, which people don't realize is a big, big deal and is going to change everything for small aircraft, which will be the aerial incubation of all sorts of new technologies that will get onto bigger aircraft.
Yeah,
If you haven't heard about Mosaic, look it up. It's amazing that the FAA is being so forward-thinking, right?
Yeah, and I would say if you work on, big military aircraft or Part 25 aircraft or whatever and are thinking Mosaic isn't meaningful for you, so you're not paying attention to it, go read over it, because it's a real insight into the future mindset of the FAA, and they went a lot farther than I expected. And we work on small programs, we work on big programs, but they just turned the lower end of the market into a big incubator for trying out all kinds of things. And, I think there's going to be a lot of good. There's probably going to be a little bit of bad, and we're going to have to narrow in on things, and that's the way the regulations always do. But I agree with Mark. That was a major step this week. And, sometimes the regulations do change and have step changes, and that just happened this week.
Last thing to mention, cryogenic hydrogen is not new, right? So there's other industries that are using it successfully. It's been transported, it's been created. Aside from its actual use in aviation, it's well understood, right? So we can learn from those.
Okay, the number one question takes us back to where some of this energy comes from in the ground. Where do we see the future of material mining for batteries, considering current practices need to improve environmentally and socially?
So I think there's going to have to be a lot done to clean up the battery industry. That is already happening with surface vehicles. So it's interesting because one of the both good things and frustrating things about having worked in electric aviation for a while is that we drive very little of the innovation in the battery industry, percentage-wise. The electric car industry and other industries really are driving the bus. And that's part of actually why that curve that I had is shaped the way it is, because we got to a point where electric cars are good enough from a performance perspective, and the gap wasn't performance or energy density, it was cost, it was reliability, it was things like that. And while the curve that I showed had very low progress, relatively speaking, batteries have become way cheaper. There have been huge advances in the metrics that matter the most economically to the battery industry. Those just don't happen to be the things that we all care about the most. So as I look at that, that's one area where the industry that is driving the bus, so to speak, does care a lot about that as we do, and there's a lot of work going on. And I think that's going to be a matter of cleaning up the process of producing new batteries, but also doing a whole lot more with battery life cycles, taking in the raw materials that are in those batteries, reprocessing them and putting them back out the door as new batteries. As the market grows, that doesn't all of that material does not have to be mined every time. There is a supply in the reuse and recycle part of the market.
In a gold rush era, the focus is not on necessarily all the accountability that should exist. And electric propulsion, whether on the ground or in the air, is in a gold rush. But there are wonderful efforts, such as Redwood Materials, that's developing recycling at scale, that's economically viable. But it's interesting the challenge that they're having, that they don't have enough batteries to recycle, because the electric cars are doing very well with relatively old batteries. They're not becoming unusable like the industry predicted. And so people are hanging on to them because even if they're only at 80% of their initial capacity, they're still mighty useful. But we will certainly see more accountability as the entire ecosystem develops into a sustainable, long future solution.
Yeah, I thought somebody might mention there was a huge lithium reserve found under the Salton Sea in California.
Yes.
So I think there is materials. I think the other question is, how do we get around using different materials? And I think there's been some promising work in quantum computing, which for quantum computing material science seems to be the leading application. And even already it's been producing magnetic materials, for example, that have no rare earths, that are competitive to existing magnet classes and ratings. So I think, yeah, there's a long way to 2050, and and things are, moving rapidly. So I think that's another theme, is just that with modularity and with, computing power in the design cycle, everything's going to speed up. There's a great chart that Keith Numbers, I don't know if you knew Keith.
Oh, yeah.
Keith just retired from AFL-CMC. And he showed this great chart that shows 23 years, 22 years, 21 years, the development of a integrated engine and exhaust system for combat aircraft. That's a long time. How can you have stable requirements in designing something over 20 years? So modularity to address that without reducing our requirements on what needs to be safe is really going to come through precisely that modularity. Because then you can have a system that's on the table, and you need a new motor. A new motor is months, not years.
Okay, I'm going to combine a couple of questions here. Aviation decarbonization roadmaps count on there being abundant SAF at a cheap price by 2050. What if there isn't?
So if there
I'd
is,
like to hear every panelist's thought on whether SAF is the long-term solution for aviation decarbonization. So you could answer,
Who's starting?
both or either one of those. Yeah, let's start left or right. Go ahead.
There we go. Yeah, so from my perspective, I think SAF is pretty important. We're looking for technologies that are future-proof, so looking at some technologies that can use logistical fuels now, but the implementation of those is actually better with SAF or alternative fuels like hydrogen. So I think SAF is definitely going to play an element. A lot of people, I think, make the argument, which I think is specious at best, that where are we going to get all the electrical infrastructure for electric vehicles, and how is that ever going to happen? Well, oil derricks didn't grow out of the ground overnight, so infrastructure with sustained demand is responded to with capital investment. That's the nature of the world. So I think as long as there's a sustained demand, it'll get there.
Yeah.
Ollie?
Good. Yeah. I believe the question is not whether it's SAF or whether it's hydrogen. I think we need both. In the short term, SAF is going to be important. Maybe it's more readily producible, even though it's a big challenge to produce SAF. But if we are, serious about decarbonization, I believe that hydrogen has a lot of promise. Okay, because hydrogen has zero carbon in it, and so when you burn it, you don't produce any CO2. And also, hydrogen will play a significant role even in the production of sufficient SAF. Especially in some places in the world where they may not have as much access to biofuels as we do here. Okay, so hydrogen itself can play a significant role in producing synthetic SAF, by combining hydrogen and carbon to produce synthetic fuel. So I think both of them have promise. That's why, for example, we think the gradual introduction of hydrogen into the aviation economy is a good way to go. Introduce it into smaller aircraft, make it possible to have multi-fuel in an aircraft where you use whatever fuel is available in a region with the ability to switch fuels, from one to the other. We produce a long-term plan for the transition and the resilience of the transition itself. Yep.
so I will say my answer to that substantively hasn't changed, but I've got a better answer for that now than I did 8 hours ago. And that's thanks to the first speaker that was on the stage here this morning. And so rather than give what I've said in the past, the aha moment for me was when he was walking through the fact that if we look at the parallels between what the ethanol industry did and the tonnage of fuel production, the number of refineries that they put on board, the feedstocks that they pulled into that, we're basically asking ourselves to do in 25 years what the ethanol industry did in 10. And when you put it in that set of terms, that doesn't sound nearly as scary. So, I think Chris made a good point that if there's sustained demand, ultimately the economics have to drive it. And in the case of ethanol, there were incentives. The economics then drove it. If we do the same kind of thing for SAF, I think we're positioned to have the same kind of results. The feedstocks are there, the capability is there, and as long as there is a long-term trend that can be invested in, the capacity will go into place and that will exist.
So it all depends on the federal government to create a level playing field, because SAF at $9 a gallon cannot compete with aviation fuel at $1.60 or $2 a gallon. And there's going to be plenty of oil around in 25 years still. So I don't think SAF has a chance unless the government gets involved.
Zero Avia's mission is to have clean aviation. So if SAF is the short-term answer, that may make sense. But as Wally said, in order to make sustainable aviation fuel, you have to start with green hydrogen. And quite frankly, if you're making green hydrogen to make a second fuel, why not just use that in the first place? So
Yeah, I want to say I support that also. I think there's going to be a transition period, and in the long term, hydrogen looks interesting, and there will be applications sooner than later, and it'll grow over time. But yeah, there will be initial people and missions and customers that need something more rapid.
yeah, the DOE is targeting about $1 per kilogram for hydrogen, and that's on par with Jet A. And sustainable aviation fuel, Mark, as you said, just needs federal buy-in, basically.
Mark, can you elaborate how the Whisper Aero propulsor can truly be scale independent? Are there no Reynolds number effects for aerodynamics?
The Reynolds number effects are advantageous to us. Yeah, if you know us, our propulsor, and you can go online and look it up, but we go to really, really high blade counts, because not only do we lower all of the noise, but we get rid of all tonal content by shifting it to the near ultrasonic. So our blades are really small, and you can think of it like the rim of a bicycle wheel, and every single blade is like a spoke, and there's a lot of them, and they're small enough that we achieve over 90% laminar flow on the upper and lower surface because we're at such low Reynolds numbers. While if you look at turbofans or propellers, essentially those blades are fully turbulent. So Reynolds numbers are friends, not our enemy.
Great. We talked a lot about hybrid electric power plants as the future. Is there room in the future market for startups and the big dogs like Pratt and GE?
Well, I guess as a startup that's partly owned by one of the big dogs, sure. Yes, the answer to that is yes.
Yeah.
But hold on, look what's just in the last 10 years. I mean, in my aerospace career, it was unthinkable to do an aerospace startup, right? 10 years ago, all that changed, and now startups have a lot of influence power, and they have much more agility and speed than any big company.
Yeah,
And innovation is key. The technology is changing so fast, I don't think the big companies can keep up.
Well, so I agree with Mark that what that means is there's a place for both, because we can move a lot
buy
fast.
us?
Well, yes, potentially, but
Invest.
at the smaller end, you can move a lot faster, you can be more nimble, there's less of a legacy business to protect. At the larger end, you've got global supply chain service and support and things like that. So there are pros and cons to both. And I think Mark brings up a good point that until about 10 years ago, we only had the pros and cons of one of those, and there was a complete void at the other end of the spectrum. Now we have a lot of business going through companies like yours and a lot of business going through companies like ours, and I think that that benefits the market in a huge way, and that that's also going to lead, frankly, to a lot of cases where the small companies are working with the big companies and the big companies are working with the small companies, because you can do things we can't, we can also do things you can't. And
exactly.
the fastest progress is when you get both.
Yeah, and it's probably just a good data point to say that I have talked with everybody here before this panel about doing work together.
Yes.
So, yeah, I think the system works. It's just a much different landscape. I mean,
Exactly.
like Mark said, that was unthinkable, but now there's a million startups. We try to look at them all. We try to talk to the ones we think are interesting. We try to work with the ones we think have value. And so, that's going to be
I absolutely agree. I mean, yes, we would not be working on hybrid electric propulsion if we didn't think there's a role for our product there, in the near and in the far future. So I agree with what my colleagues here have said, and we don't view ourselves as competitors necessarily. We view ourselves as collaborators in terms of, because whatever they learn from what they're doing, we can learn from it too. We can leverage that, and that goes both ways. Yeah.
And they're really good startups we just buy.
That was my point.
That will happen. But then there will be a circle of life also.
That's it.
I will say the current wave of startups, at some point, probably a lot of them do get acquired and get rolled into the global infrastructure of the big companies, and then you get the next wave of startups going. And I think that's something that didn't used to happen, and now if we keep that going, that's going to be a healthy balance.
The interesting thing is if a startup gets enough momentum and capital, like Joby, I don't think they can be bought, because they have visions of being $1 trillion company, and they know they're going to move faster and better without being bought. So I think you're going to see some new
aerospace primes.
giant aerospace companies.
I think it is kind of binary. You're going to see the companies that are on a trajectory where they can IPO and be their own thing forever, and then you're going to see companies that probably favor growing to a certain point and then becoming part of something else. So they're both valid paths.
But for any of you younger people, it's like the capital creation that's happening is amazing. And it's like, why would you work at, NASA, which I did for 32 years, or a big company, which is an institution with so many processes that are so frustrating, when you can get equity in a startup that's going to be worth 100 times as much in 5 or 10 years? It's such an amazing time to be young.
The views
I'll just add
expressed
on.
by Mark do not reflect all panel members.
I would change will be to could be.
Could be.
Also,
I'm not going to say what
it is-
Mark said. I
it
will
is roulette,
say send
it's
us your
gambling.
resumes. So yes.
Hey, in the last minute that we have, I'm just going to go down the road. Give me 15 seconds of what excites you the most about the next 25 years.
My first? What excites me in the next 25 years? Just the ability to make a change. I think, as we just said, the market is changing very quickly. There's new technologies coming out every few years, and I think there will be some major shifts one way or another.
Mark?
So I've spent my entire career trying to achieve one bigger objective than even electric propulsion or vertical takeoff and landing aircraft. And that is to create a new Wright Brothers era. And you guys are living in it. Jump into it. It's an amazing time to be young and be an aerospace engineer. The future is autonomous. It's amazing new ways to manufacture with additive. Every single part of aerospace engineer is going to be on the frontier of these technologies, and you get to be part of it. I wish I was young again.
Eric?
So I think the thing I find the most exciting to watch is the fact that we've now got a huge array of technologies that I think 25 years from now are going to go from being novelties to mainstream. And if you go back, there was an era in aviation, particularly commercial aviation, where I'll say each new generation of product was the last generation, but 7% more efficient. And if you were to take your average person out at the airport here, and you took a 707 from the late 1950s and put a fresh paint job on it and rolled it up to the gate, the average person in the terminal would say, oh, there's a brand new airplane there. That's great. They don't look different. It's a tube with wings and it's a jet. And of course, those of us here know the difference between low bypass and high bypass turbofans. But the fact is, things haven't changed dramatically. And so the thing I find exciting is that pace of change that I think has been kicked off by all of this work that's going on. And it hasn't yet hit the market. So it's not mainstream yet. And I think 25 years from now, aviation is going to look drastically different than it does today in a way that is bigger than the difference between today versus 50 years ago. And that's exciting.
Thank you. Wally?
Yeah, for me, the exact, this is the best time in aerospace industry. And for me, what's exciting is to know that the things we are working on now and the things that other people are working on now, some of which we argue whether they become reality or not, we actually become reality in 25 years from now and beyond. So the excitement of thinking and knowing that the world as we know it now will continue to change and change even more drastically than we have witnessed, is really exciting indeed. Just like Eric said, a lot of things, we at Thanksgiving, I think 2 years ago, we were on the dinner table and I asked, my kids were on the dinner table, and I asked, how many of you will take an autonomous taxi? And they all raised their hand up. They will, but my wife will not. So, it's an indication that the mindset of the public is evolving as they see these technologies being deployed. And 2 days ago, Brian Yutko shared that, he's sometimes more comfortable with an autonomous car driving him to the airport, than with an Uber with a real human being as a passenger, So some of these things that we think are not very convenient and comfortable are going to become the mainstream. And we are going to live to see some of this happen in our lifetime.
Right. Yep. Closing comments, Chris.
Yeah, I'd say that I'd go back to the crazy drawings I made of airplanes as a kid, and even as mature a little bit, and it's totally different from what propulsion and aircraft are today. But then you go through college, you spend years of your life going through college, getting educated, getting a master's degree, whatever it is, and you get out and you work on very incremental improvements, and it's kind of disappointing. Now, I've always worked in advanced design and research and development, so I've always been thinking farther downstream, technologies that are TRL 2, even just clean sheet. But seeing things actually start flying is pretty damn exciting. See things in the air and flying, and that we're actually doing it, and we're looking at, again, because we're kind of blowing up the turbine to some degree, ripping out its heart, and we're reshaping that into something that's, from every aspect, from combustion to just flows, to materials, to the structure, implementing all types of different materials, design, supervisory controls. It's a fun toolkit to play in, and the results are going to be amazing. So I think that's what's exciting to see it fly.
Gentlemen, thank you for your participation this afternoon. Great panel. Thank you for what each of you are doing to accelerate propulsion for 2050. Audience, thank you for your questions and participation this afternoon.
Cheers.